Okay, hi. Can you hear me on the back? I'm Lewis. I've been at Google about 4 years. I work in the AdSense platform and the front end for publishers. I've been doing data processing pipelines for about 2 years, the last 2 years or so. And obviously Google this is kind of core to a lot of what Google does. So I'll take you through some examples of projects that I work on and how we use data processing pipelines to make the user experience better, the kind of analysis we can do with it, and talk through some of the technologies behind how we work. Cool. So maybe a quick show of hands. How many of you have worked with like kind of batch data processing pipelines before, or used like Hadoop and things like that? Okay, maybe like 30%. Okay, so let's start off with an example. So working AdSense. So you know what AdSense is? It's a platform where if you have a website and you've got lots of traffic, you want to make some money, Google will help you put ads on that site. We provide you with the tags, we run the auction, we make a lot of people buying the ads, and everybody's happy, you make money, we make a bit of money. So in this case, the AdSense front end is where you go to manage all of your ads. So we run a service which generates these cards in the UI, and these cards are there to kind of recommend certain actions you can take to help you improve your like how well your site's performing in terms of monetization. And we're reading all kinds of data sources. So in Google, we log everything, and we store all the statistics and all kinds of data sources, and we're combining all that together, trying to detect scenarios where we want to help you make more money, and then building these cards, which we then search in the front end. So this is what they look like. You just about see that. So if you're on the AdSense page, you get these cards down the side. So for example, here we've got up to 10% predicted increase in weekly earnings. Enable your ad units to display text and image ads. You can make this change now, or you can create an experiment. We have in total probably about 7 pipelines which are running in the background to build the data, the various data sets over weeks to come to the conclusion that doing a certain action will have some benefit to you. So the other ones here, we've got a recommendation about removing the borders from your ad units, or a recommendation about adjusting the placement of the ad on your page. So we are crawling all the data we have, and we're working out where the ads are positioned on your pages, and then we're telling you where you can move them to make more money, or if you're getting some bad experience because of the position of the ad. So why do we need a pipeline? Why can't we just do this in the front end? The main problem is there's a lot of data which we want to look at, in particular logs, which is not in a MySQL database or anywhere where we can do lookups. It's just straight up raw data dumped out and put in files somewhere. And we need to kind of go through that and work out whose logs apply to which publishers, and decide what actions to take. So we can't really technically do it at a certain time. We can't decide what the content of these cards should be. So we need a pipeline to do all this analysis for us. And, so yeah, there's many data sources which aren't queryable at serving time. And we also want to track things which aren't necessary to do with the user's interaction with the AdSense front end, or measure rather. So we want to detect when the recommendation is active. Let's say you put an ad in a strange position on your site, but you never logged in. We want to know when that happens, and then we'll tell you that you should move it, and then we want to know when you did it, and then we'll probably wait a few weeks to look at how much of an impact that had on your website, so we can kind of feed all this back into our pipeline and provide a better experience. So it makes serving the cards super simple, because we've dumped just the data we need in a table which we can serve very quickly. We don't need to do any lookups or querying. But to create these recommendations can take maybe 24 hours, maybe more, depends how often the pipelines run. So there's pros and cons. So, okay, who knows what map produces? Quite a lot of people. All right, so I'm going to walk through. So core to a lot of these technologies is, of course, MapReduce. I'm going to give you a quick overview of what it is, how it works, maybe quite quick if most of you are familiar with it, and then kind of see how we use that to do some of the things we do, what kind of problems we run into. Okay, a programming model and framework for processing and generating large data sets with a parallel distribution algorithm. So how does that actually work? There's three main stages of a MapReduce: map, shuffle, and reduce. The shuffle isn't like a real stage as such, but it does have a purpose. So the first thing you do, let's take a huge data set, and I'll show an example next. We want to map all of the data that we read into a particular key. So for example, let's say I want to, well, let's look at the example. So we'll map all the data to particular keys, and then we have a shuffle stage which gets the data into the right shards, and then we have a reduce stage. So we end up with something a bit like this. So in this case, we want to count cats and dogs and things. Let's say our input data is a huge list of words or a huge list of sentences, and we want to count the frequency of all of those words across all of those sentences. So we call each of these like rows in the first table like a shard, and a shard could have like lots of data in it. In this case, the first shard is like the word cat and the word dog in it. So our map stage is going to map every input, so each word to the word that it is, and just simply the number one. And we kind of expand the original data. So you could map if our single input is actually a sentence, we could map it to multiple outputs, so multiple words, which is kind of what I'm illustrating in this example. So the next stage is we've got all of our pairs, key value pairs, and we shuffle them. This kind of happens naturally, and the point of this is to get everything with the same key onto the same reduced shard, so that when we come to actually process the data, we know that every unit of data which was for the entity cat is going to be running in the same shard. And that's the end of the shuffle gives us something like the multiple cat and the number one pairs. And then finally we run our reduce. So in this case our reduce is really simple. We're just going to add up all the numbers. And we realize that there are 3 cat words and 2 dog words and a mouse. So Google's obviously got its own kind of internal cloud thing. I won't go into too much detail, but you can deploy machines, tasks, and there are lots of machines out there available for you to use. So the MapReduce ends up with a structure something like this. We run our user program, we define our map functions, our reduce functions. That program is going to spawn a master, and the role of this master job is to kind of sit there and watch all of the workers on the map side and the reduce side, and make sure they're okay, make sure they're not getting stuck. If one of them crashes, then it will restart that worker. So it's kind of just in control, making sure the whole thing's running. And you can see our input is 4 shards of data. The shards aren't synonymous with workers. You could run a MapReduce of 1,000 shards across one worker if you wanted. It would be quite slow. You can't have. It doesn't really make sense to have more workers than shards. If that makes sense. The shards will get distributed to the workers, so you can't parallelize any more than that. So each worker gets a directive: process shard number 10, and put your output into this intermediate storage. And then once that's finished, the reducers will get fired up, and each shard will say, okay, well now I'm reading this, I'm applying this operation. And you end up with this, in the final output, you have this kind of rule that the number of reduced shards you have is going to be the same as like your output data set. So if it's not clear what I mean by sharding, I mean, it's basically if I've got any data set, any large collection of objects, I just split them into n roughly equal chunks. And that's all that we've got going on here. Obviously, it's clear why that would help with parallelization. If you can fit into this framework, this map and reduce framework, in theory you can scale, and you'd be amazed, like most operations you want to do, you can find a way to fit it. The shards are split between lots of workers, obviously it's very parallel. So ideally, some requirements to make sure it all ticks over smoothly. You want to be able to shard your input. If you can't, it can be troublesome. Trying to run a map use over like a MySQL database, which aren't typically sharded, it can be hard to make that work. So you want the shards to be roughly the same size as well. If you've got one shard of data which is way bigger than everything else, then 99% of your shards can complete, and then you're sitting waiting for this one guy who's still turning over a gigabyte of data for some reason, and then you've got a bit of a problem. So the sharding is kind of really limits how much you can do here. In this case, if you've got 10 gig and you're trying to do a map reduce where your output is going to be in the order of 10 gig, you've only got 5 keys, each key contains 2 gig roughly. You can't really parallelize that very well. So think of an example where this like doesn't work. Often in any platform you're going to find you've got some users or customers much larger than others, they have a lot more data. And if your key that you decide to process them on is the customer ID, say, you're going to find some have a lot more to do than others. So usually you probably find that if it's really extreme, then you can find the problem. And then you probably want to find a way to split the data within a single customer up. And then you can kind of, this is like a pre-aggregation stage to distribute the work a bit. Okay, so MapReduce is cool, you can do a lot with it, but I want to do more. I want to run 10 MapReducers. I don't want to create 10 binaries and like 10 scripts, wire up 10 different data sources to all read one from another. So that's why we have this thing called Flume. So all of this stuff, MapReduce, Flume, everything I'm talking about is all in papers that Google have released. So the links aren't going to be very useful, but you Google Flume Java paper, you'll find the paper I'm referring to. So here we can define much more complicated graphs of operations. So I've got 4 inputs. Each of these letters is just some, say, simple operation on that data. I've got a flatten in the middle there, which is kind of just means join that data together, or just group it together. I want to do a count, just like our cat, dog, mouse example. And then finally, I want to do like a join, like a SQL join. If you think about it, a join in the MapReduce world is basically a MapReduce. You can have a MapReduce process multiple inputs, and as long as you shuffle them by the same key, they're going to end up in the same shard. You can make sure you know which one came from where. So this is effectively how you do like an inner join in a data processing pipeline. So we can look at this and we can kind of realize that there's really fundamentally 2 MapReducers. We need one to do counting because it requires some kind of group by key. And we need joins because we need some kind of group by key. So we're going to have 2 MapReducers. But to define this as a sequence of MapReducers is going to be difficult. Well, it's going to be awkward. You're going to have to make sure it all fits together nicely. It's a pain to maintain. So Flume allows you to define these kind of sequences, these graphs, and then we'll do all the optimization and work out how many map reducers you need. It will pack down like subsequent operations together into a single map function. So again, this is from the Java paper, and we start with our original graph, and then we get something a bit more complicated. So it's worked out that we need to group by key for our count and a group by key for our join. It's tagging stuff, so this is what I was saying about the joins. You want to know where each thing came from. So join is just like a flatten and a group by key. Anyway, the point is we don't have to worry because Flume is going to do all this for us, and then at the end it's worked out that we've got two top-level map producers that we use that will have to run back to back, and it's concatenated all the different operations together, and it will run this pipeline. It will actually fire off the map producers, it will wire up all the inputs and outputs to make sure the whole thing runs through, and then provide you with a nice UI to monitor how it's doing. So this is kind of what Flume code looks like. Flume Java paper. You can see it. So we put up three stages, I guess, on map, shuffle, and reduce. And we process objects called P objects. We've got P tables and we've got P collections. P tables are kind of indexed, I guess, key value pairs. And P collections are not, they're just arbitrary collections of objects. So in this case, we've got words is probably a P collection. We're going to apply a parallel operation. We define this do function, which says convert a string to a pair of string and integer. So this is exactly what the original example does. We emit a pair of the word and the number 1. And we say that the type of this output is going to be a table of strings and integers. Flume is kind of, in this example, it's kind of being clever. It knows that if we're removing a pair of type A and B and we define our output as a table of type A and B, that it needs to be to a new P table type. And then we do our shuffle. So we just say group by key. Now I've got a string, which is my key value, and I've got a whole collection of numbers. In this case, my collection of integers is just going to be a collection of number 1, because it's a trivial example, but you can do more interesting things with it. And then we've got some built-ins. So we want to combine these values, and this is effectively our reducer. So we combine all of our collection of integers, we sum those integers, or we can just count the length of the collection in this case. And then we end up with our parallel collection of, our parallel table of words and count. And we can do something else with it. So all of this stuff is running over the network, and you need to be a little careful about the kind of data you use. For example, some types of serializability are slow and painful, and this is why, I guess, one of the reasons why Google has protocol buffers, which probably many of you have heard of. And these are kind of built for network things. So they serialize very quickly. You can put a data set with a protocol buffer from one language and read it in another, and it's totally language agnostic. So because you're doing network stuff, even though it doesn't look like it, it looks like I've just written a bit of Java code, you need to be careful with that. And we generally stick to protocol buffers and like primitives or other like specially optimized data types. Cool. So it's an abstraction layer on problem map use, basically. It makes your life a lot easier, and it really is easy. In 20 lines of Java, you can define and run a 4-stage like Flume pipeline running God knows how many map producers. It optimizes the structure for you, and in the paper they show these examples where they compare the performance of an optimized Flume pipeline versus a kind of hand-optimized series of map producers, and the development, the speed is basically the same. It will do clever stuff like execute small parts of the pipeline in memory. So if you're if you're starting out, say, and you want a scalable system, but you don't have any scale yet, it will realize that your input data is only 10 megabytes, and it will just run it in memory. It won't bother actually firing off, sending the data to a load of other machines. And it's really, really cool. I've got some more examples. So I would argue that it can be a leaky abstraction sometimes. You've got to be careful with it. A good example would be if you think that you have a P collection and you want to remove all of the duplicates, then that could be as simple as writing one line of Java saying my P collection dot remove duplicates. And what you've actually done is caused an entire new map reduce to get inserted into your pipeline, because that's the only way you can remove duplicates in a parallel way. And before you know it, you've got some horrific 20-stage Flume pipeline, and it takes 10 hours to run. And I see that all the time. So you do need to know, you do need to understand what's going on behind the scenes. You need to understand roughly what MapReduce is and how this thing's going to run. But in general, it's an incredibly useful tool. So there's an additional feature that Flume provides, which is pretty cool. It's side inputs. So sometimes you have a common data object which you want to be available in all of your worker machines for every shard. So, for example, if you think some kind of map, and it's not something that you can actually just write in Java, but it's big enough that it needs to be computed. You can define these side inputs and load them up in memory for every single worker, so they will have those available to you. And that can be really useful for performance. There's nothing you can't really do with it if you think of it as a very general framework. We have some pipelines which will just do a map, basically, and they'll use that map to call the service in parallel and do that quickly. So you can do pretty much anything. Okay, so far I've talked about batch pipelines, and I'm going to talk a little bit about continuous pipelines as well. So this seems to be a shift that people are generally interested in. There's a lot of benefits, some downsides. So when we're processing batch, I mean we're going to run our pipeline, we're going to kick it off, it's going to take a few hours, and we're going to run it every day, say, or maybe every hour, whatever. So the problems here, it can be quite high latency. You're generally looking at a few hours at least to get from beginning to end. It's harder to monitor. You've got spiky kind of load on your systems, and it's hard to always identify where something's going wrong. Jobs kind of spawn up and process data, and then they get shut down and they disappear, and it failed and you don't know what happened. And the load on resources, I mean, obviously Google has a lot of resources, and it's not such a big problem because if there's 100 teams doing this, it gets spread out. But if you're trying to do something like this on your own kind of private cloud, then it can be a bit of a waste to have all of these resources when you're only going to use them for a few hours a day. So in a continuous world, we're kind of talking a very similar kind of architecture and framework and API, but we need to make some small tweaks so that the data can be handled in a streaming way. So when I say streaming, I mean like PubSub is generally what's driving a lot of these pipelines. You spread your load, the job's always running, you can monitor it easily. It does make some things like joining data together trickier. So if I have merchants and I'm trying to join them by some key. And every time I get a new customer, I get a PubSub notification. But every time I get a new merchant, I get one as well. I need, if those things don't happen exactly at the same time, I need to use kind of, I've got a time aspect in there. So maybe I need to remember things basically and store kind of cache of where I am. And it can make the code a bit awkward. So here's an example. So this is Cloud Data Flow. This is something we announced at I/O. I don't work on it. I asked the guy who does for this slide. Well, actually, I think this is from the blog post. So this is effectively, I think, supposed to be our offering to external people for like flume-like behavior. And we've got some similar code to the Flume code before, but we actually see the structure of it here, not the kind of details. So we're defining our new pipeline, and we're streaming from a PubSub source. We've got some collection of strings. We're going to apply some transformation. So in this case, this is not clear what that transformation is. Key tweets by team. So we've got the team is now our key. And we're going to calculate things like average sentiment. And the Cloud API interface gives a nice kind of overview of the structure of the pipeline that you created. You can monitor it, you can see how it's going. And this thing's going to stay there. So it's a simpler example. You've only got one stream of data. Compare this to running your own like Hadoop MapReduces. Google's kind of taking, it's a much higher level of abstraction, I guess. This is going to be running Google's cloud and Google's infrastructure. You just need to write the code, and you just get charged for what you use, I guess. I mean, this is kind of true. This is kind of a pattern that's true of everything you do at Google, it seems. You're so disconnected from actual hardware. You don't have to worry about machines, really. You're a few layers up, and I guess this is very similar to that. Okay, so some general advice. Maybe these are just things that I've done wrong in the past, and I want to warn you about. So we modify write cycles that are generally annoying and have caused us lots of problems before. So we have our card data source, our big table, and we want to update the cards every day. So we reload the cards in and we calculate what's changed. Maybe some parameters of the card have changed. And then we want to rewrite it. I mean, this is just a nightmare because you ship one thing wrong and you've just deleted all of your data or corrupted all of your data. So there are ways around this. I'll go through them. So don't try and. We had a system where we generate daily data sets every day. And then we'd have other jobs which would run afterwards and say, okay, well, I need yesterday's data for this data set. And it wouldn't be there, and it would get upset, and it would explode. And you basically get this big system of cascading failures. So the trick here, really, relational databases is kind of realizing systems like the table where you effectively have timestamp data stores. So in our case, in our cards case, we create all of the cards fresh every day. We write them to the big table with the same keys, but they get a new timestamp. So they just kind of layer up. If we mess something up, it's very easy for us to clear them out. Okay, so I told you a bit about Cloud Data Flow. And obviously Hadoop is out there. I won't pretend to really know much about it, but I'm sure some of you use it already. Crunch is, as far as I can tell, supposed to be Apache's kind of offering, which is a bit like Flume. If you need to do something more than just run a single MapReduce, and there is, of course, lots of other alternatives.
Any questions? Any questions?
Yeah. It seems that Spark is provides the same level of abstraction of the MapReduce process, right? What do you think is the difference between from Java and Spark or Storm?
And what, sorry?
Storm. So Storm is data processing on the fly, right? So I think, can you say that from Java is combining the Spark and the Storm?
I'm not familiar at all with them, so I'm really not sure. Yeah, sorry.
Any other question? No questions at all? We have cardboard for good questions. Any questions? Okay.
I saw in your advice slide that you dislike relational data quite a lot, and I was just wondering if you'd seen any sort of advances in relational databases as every couple of months you see just a couple of newspapers here and there about some relational database achieving scale or performance that have been previously only thought capable in non-ACID databases instead.
Yeah, I won't say that I have a strong opinion about SQL or no SQL. I know most people seem to. I think purely from a practical point of view, we do have some relational databases at Google, and I have had to write data processing pipelines, particularly MapReduce into Google. And it doesn't matter how hard we try. And Google has obviously made some very scalable relational databases. We always seem to run into problems, and it is a pretty textbook thing to just always work with a big table, just because it's just kind of built for that. It just works really well. It shards really well. The shards kind of look weird, or tiny servers when load on a particular tablet gets too high, for example. There's a whole paper on it. You can read it. So yeah, I wouldn't say that it's a no-no. I'm sure there are databases out there which will handle this kind of thing well.
Do you want to get the cardboard?
Sure. Yeah.
That's
a good question. Yeah.
You want cardboard actually?
How easy is it to add specialist stages into this software? For example, geographic sorting.
Yeah, stuff like that's tricky. I guess in that case, your key isn't well defined. When you're trying to do stuff like that, you kind of have to improvise a bit. So we have some scenarios like that where our key isn't a very clear ID, and we can't just bucket stuff. So often what you do to handle it in parallel is try and group to a kind of larger area which you're not too worried about the border overlap, and then within memory you can kind of do the more complicated stuff within that shard. So yeah, we have had to deal with some things like that before. It's a pain, but it's doable.
Was that a good question?
Yeah, it's a good question.
Just hand it over, please.
On the last slide, as part of your well, we're not on that one,
Okay.
As part of your tips, you said don't rely on specific, daily updates on a batch processing pipeline, right? What if I actually only need the daily update on that? Why would I even then go for continuous?
So maybe that was misleading. There's nothing wrong with running stuff daily. I think we do that all the time. I think the problems that we run into in particular are kind of relying on a set of data being there every single day, and having a pipeline to build that every day. With pipelines generally, you're not monitoring them as well. They're a lot harder to keep alive, and your pipeline fails one day, and then you you're missing that data set, and if you're not prepared to deal with that, then everything starts to break. Which is, I guess, I was more advocating for kind of like timestamp data sources. So, for example, we do still generate daily dumps of data, and not use Bigtable. There are actually dumps of data, but you want to make sure that anything reading that is not going to expect something to exist for a particular date, and you have some kind of utility. So, give me the latest version of this data set. I guess that's the kind of interaction you want to go for.
Obviously, the results of running these pipelines are quite large as well. Well, maybe not obviously, but I imagine they are. So can you give some examples of the kind of techniques you use to actually check you've actually got the right result?
Yeah. So in a lot of these frameworks, you can, so in Flume in particular, we have this kind of counter system where at any point in a map or a reducer, you can like increment some value, and this kind of all gets passed up to the master. So then we can, when the job finishes, we can export those somewhere, and we have some kind of system checking that, you know, we got the expected amount of results out at the end. We have a QA system as well, obviously, and you know, you can unit test these things quite well. Surprisingly, it will let you run something in memory. But in general, I think we actually rely on the monitoring and counting the counters quite a lot. So I can work out exactly how many outputs and any other kind of characteristics of it, and then set up those rules to say, you know, if you didn't generate X many values, then something's probably gone wrong, and you should go and have a look at it.
Okay, so you have a predetermined idea of what the answer actually is then, rather than a statistical.
Yeah, there's nothing. Yeah, it doesn't kind of transform through time. It's nothing clever. It's very easy to change the numbers. So you usually set up this like accepted thresholds, and if it goes over, you investigate. If you're happy with it, you change the thresholds and carry on.
All right, thanks.
Can you hand it over? Any other questions over there?
I was wondering if you have very data-heavy workloads, so you have a stream of tasks, and those tasks read a lot of data and write a lot of data, and some of that might be overlapping. What kind of technology would you recommend for dealing with such workloads?
Streaming tasks. Do you mean? Can you elaborate there?
So you have a distributed architecture. You have basically a message queue or some form of task dispatcher, and the tasks you're dealing with are very I/O heavy. So you read lots of data, you write lots of data, and some of that might overlap. So there's potential to reorganize tasks to optimize for I/O. Do you have a specific technology you would recommend for that workload?
Yeah. So as I understand it, there are some mechanisms within Flume to kind of, or within MapReduce in general, to kind of identify these situations where. So if you looked at a MapReduce running, for example, you could probably determine that it was heavily blocked on I/O, and then you got a few options. I think in some like really custom scenarios, you can even kind of have a liquid sharding where it will break those pieces up into more, or you can even just assign it to a more beefy machine which has got more CPU. So it does try to work some of this stuff out. I've never found personally that I/O to be a major issue. I mean, generally you just keep cutting the data until the chunks of data that you need to process is small enough and it's not a problem. And things will probably usually be on the order of like 100 megabytes or something.
So you would say MapReduce is still fit for that?
I'd say so, yeah.
So the time's up. So thank you, Liz. Before you leave, there is